Hi everyone, I'm TonyLouis Veberi, and this summer I was working with Dr. Francisco Navarro on classifying galaxies and predicting their black hole masses using machine learning models which we trained. So the general outline of this talk is going to be I'll give an introduction to what machine learning is and the method of training that model, as well as some discussions on the key parameters to take note of when doing the training, as well as the next steps and the conclusion. So the motivation of this project was, as you see on the extreme side here, that's an image of a galaxy. And our aim is to train a model which is able to take certain key properties from this galaxy and further predict the black hole mass of the black hole which is found in that galaxy. And so the special class of these black holes are called supermassive black holes. And they're about a million times, 10 million times massive than our sun. And the reason why we chose this class of black holes is because they are directly related to the properties of the galaxy in which they are found. And so this equation is showing the function which is going to be which is going to be used by our model in order to correlate the input properties of a galaxy and probably predict the black hole mass. And so why do we use a machine learning algorithm? The first reason is in higher dimensions, it's very difficult for humans to comprehend correlations between like input and predictions. And also machine learning algorithms are data driven. So the most important factor we should be considering is what data and how helpful is that data for the machine learning algorithm to make sense of it. And so here is a general structure of a machine learning algorithm. So using our input data, for instance, the galaxy which we have, you're going to see the most important thing is to prepare the data in a form which is comprehensive for the machine learning algorithm. And then we pass it through the model, which I'll talk about later. This is where we actually did most of the training phase. And so after you do that, it's up to the machine learning algorithm now to do the predictions for us. And at the same time, we also prepare another set of data called the validation set. It's exactly the same data, but we don't set it up for training. So this is going to be used to tune parameters. And so the tuning of parameters is simply like it does a training, like it does a trial training, and then finds the best possible parameters, which could then be used to do the actual training of our data in order to get predictions. And also, in some cases, when you get your prediction, you may not necessarily want to test it on the entire data to see how well the algorithm did. So you could also just take a slice of your input data and use it as your test data to see how effective your trained model worked. And so this, I've been mentioning the model, and so this is the general structure of most models. And so you find an input layer, a hidden layer, and an output layer. And one thing as well is that there could be several like number of hidden layers. And so this is where the various types of models come in, because there are tons of, like there are hundreds of models which could be used to perform a given task. And so what makes all these models different from each other? The number of hidden layers, and these layers tend to have neurons, and these are what do the actual like the predictions and the finding of the patterns. And it also has activation functions. These are mathematical functions, which I would call them, they're malleable or flexible in the sense like these are templates which could be further shaped in order to understand the pattern of our data and then give its own output patterns. Okay, so when we did our first training of our model of our machine learning algorithm, we tried a function like the one you see here, this trigonometric function, and we had a good prediction. And so the plot on the green is actually what our model trained and predicted, and the one in orange is a true model, which we already knew before input into the algorithm. And so the next step now is how do we monitor and how do we know, like before even visualizing this, you could actually do a test. There's a method in which you could know how well your algorithm is performing at whatever given time. And so we call it the loss function. So this is going to take your prediction for every input step and compare it with the true value, which you already had before doing the training, and see how much of the deviations you had. So we call that the loss. And so on this extreme side, lots for our validation and our training data. And so we could just focus on our validation data because it gives us the same information. But I was just giving those two possible plots because they are alternatives which you could use to track the effectiveness of your model. And so you'd see at the very start of the training, that could be epoch 1. At the very first epoch, you have so much loss because the algorithm is still like that. It's still just introduced into the training. But the further it goes to about the 1200th step, you'd see it becomes very accurate and the loss is as minimal as possible. Okay, and then the next question you'll be asking is, when we do the training and we then do predictions and we know there's some progress, how could we facilitate the improvement of a machine learning model? And so there's something called hyperparameters. It's basically parameters which has done a pre-training, like these are outputs from a pre-training process which we used a validation data set with. And so when you get those hyperparameters, you could conveniently use them in your actual training and you're guaranteed to have a better performance of your machine learning algorithm. And also the architecture of your model also plays a big role. For our case, we had fully connected layers. So this is like a general graph which shows you the comparison of the performances across several machine learning models. And so using fully connected layers, AlexNet seems to be the best in performance for our case. But if you go to other scenarios where you want to use images and you not necessarily need fully connected layers anymore, then higher performance models would play a better role, like the C1. So the next steps of this project is we have succeeded in having a working algorithm which is able to give us like accurate predictions of mathematical models. And so our next step now is to use the CAMELS data. This is a suite of simulations of large-scale structures in the universe. And so from this data archive, we're going to take it already has pre-prepared the properties of several galaxies, and this is simulated data. And from those properties, we can be able to predict the black hole mass. And so there are about 30,000 galaxies we'll be working in at the end using the model we've just trained. And so this was just another trial we did because we have worked like the previous result I showed, which we got the mathematical prediction using a trigonometric function. You see that works with numbers. So we also wanted to try if this can also make if this is effective when we use images. So we took the Sloan Digital Survey data of galaxies. And so these are galaxies with labels. And these labels are like the classification of these galaxies, which are manually done by astronomers. So what we took our machine learning algorithm and made some changes using the model we trained to see if it could also recognize certain patterns and do the predictions of the galaxy types on its own. And so when we did that training, we realized like this is just the test region we use. So it would be costly to be doing the to check the output for the entire data set. So we took a test slice and these were the predictions we got. And so overall, when we did it when we calculated the accuracy for the entire data set, we had an accuracy of 90% for using the AlexNet model. And you see, in some cases, it perfectly got all the features we wanted. And in some cases, it deviated by 1 or 2 or all of the features we expected it to. And that's the loss function, which tracks the progress of our machine learning algorithm as we did the training. And just in the previous image of the loss functions, the x-axis there indicates the epoch. So those are the number of steps which the machine, because this is a looping process. For every possible step, it does a training and does a prediction and goes to the next step. And so the epoch is a x-axis which keeps track of the number of steps it's doing, and the y-axis gives us the idea of the loss function at every step. And so in conclusion, we have been able to use this model to handle supervised learning cases where we know enough about the input and how the output should look like. Like for instance, the mathematical function we gave it, we already know how that function looks like, and we're comparing with the output of a machine learning model. But with the CAMELS data this time around, we don't have a clear understanding of the relationship between the black hole masses and the galaxy properties. So this time around, we're trusting our algorithm to be able to understand these patterns because we have tried it on systems in which we understand enough about it. And so in that case, we call it an unsupervised learning case. And so the next steps of this, as a conclusion, is to be able to confidently go to the unsupervised learning cases and recognize patterns in order to predict black hole masses. Thank you very much.
Okay, in the room, are there any questions for Tony? Yeah, Jameer?
The black hole masses, those are one of like the because of their mass, they give a lot of properties which could reveal like new physics or give us a new understanding of how like gravity works in several structures in the universe.
Other questions? Carlton?
Knowledge of galaxies is very, very small. So do you know if like interactions? Because I know that sometimes galaxies may, like, interact with each other. So do you actually um have a way to account for like local interactions between galaxies in some of these machine learning models?
Exactly. It's possible to simulate like, using the camel's data because that's a simulation of galaxies. So you're able to understand the evolution of certain properties when galaxies move closer to each other in your simulation.
Thank you, and thank you for the talk.
What about on Zoom? If there are any questions, you could unmute and ask. Okay. All right. So let's thank TonyLouis again.